So an element is a pure substance, but an element can be broken down into atoms. And an atom is the smallest piece of matter that can still be considered a portion of that element. If we start to take atoms apart, then we're going to lose the properties of that element. So each element has a unique atom. And these atoms are made up of subatomic particles. And if you're taking chemistry, hopefully these are going to look familiar. So neutrons are going to be neutral. NEU neutron, NEU neutral. So they have no overall charge, and these have the mass of 1 atomic mass unit. A proton has a positive charge, P for proton, P for positive, and these also have a mass of 1 atomic mass unit. Both the neutron and the proton are found in what's called the nucleus. So that's right here, the center of the atom. And this here is just 2 different representations of the same atom. So you can see in the nucleus of this one, it has 1, 2 neutrons, which are brown because apparently that's a neutral. And then it has 1, 2 protons, pink protons, positive charge, going with a P sound here. And then the last subatomic particle is the electron, which has a negative charge. I don't have a fun alphabetical way to remember this one. You just need to remember that electrons are negative. And electrons exist on electron shells. These are sometimes thought of as a cloud of electrons. So you can see this one's kind of drawn the electrons out here. The electrons are always moving. The uncertainty principle means that we either know where something is or how fast it's moving, and we don't know both. When we draw electrons, we're just kind of guessing at what they're doing at any one time. The cloud view isn't super helpful for conceptualizing electrons, so I'm going to do these kind of Lewis dot structures where we draw the electron shells. The molecules that we're going to look at in biology are only going to look at the first 3 electron shells. So the first electron shell, and I'm going to just use E minus here to represent electron, can only hold 2 electrons. The second electron shell can actually hold 8 electrons, and then the third electron shell can also hold 8 electrons. This is important. You're going to want to remember this not only for chemistry, but for being able to answer questions about how interactive is a molecule going to be, how full is its electron shell. It goes 2, 8, 8. We have a lot of different numbers to describe an element. The first one is the atomic number, and this is the number of protons, so P positive for protons. So let's look at helium again. Helium, you can see this is 1 square from the periodic table of elements. It has the symbol here, He, and then the atomic number is usually the biggest number. It's written up here at the top. In this case for helium, the atomic number is 2 because it has 2 protons. So we saw a picture of helium. In the nucleus here, we've got P plus is equal to 2. The mass number is the number of protons plus the number of neutrons. In the case of helium, I know that it has 2 neutrons, so the mass number would be 2 plus 2 is equal to 4 atomic mass units. And then the total atomic mass is going to be everything, so protons plus neutrons plus electrons. And you can see in this case that's 4.003. So if you do the math real quick, that means that the electrons only weigh 0.003 for the element of helium. Electrons weigh so little that generally the mass of an electron is negligible unless you're looking at something that has a lot of electrons. The atomic mass can almost always, at least for the elements we're going to cover in this class, be estimated and rounded down to the mass number because they're really not going to have much mass in electrons. So you do need to know specifically the atomic number is the one that I'm going to focus most on because this is going to relate to the number of protons. The number of protons defines an element. So all helium molecules will have a proton number of 2. If I change the number of protons, I am talking about a different element. So if I'm talking about something that only has protons of 1, that's not helium anymore, that's hydrogen. The mass number and the atomic mass can change. Elements are able to gain and lose neutrons. Elements are also able to gain and lose electrons. So the mass number and the atomic mass can change at any time. But the atomic number of an element is never, ever, ever going to change. And most of the time, the atomic number is also the same number of neutrons. So here's a periodic table of elements chart that is akin to what we would have hanging up in a classroom. And you can see in the top corner here, you can see the atomic number. Down here, you can see the total atomic mass, and then the atomic symbol. I'm not going to ask you to memorize atomic numbers. You're always going to get the atomic number if you need it, or get a picture of a periodic table if you need it. But you should be aware that every single element has a different atomic number, and that is because every single unique element has a different number of protons. Isotopes. So protons are the only things that cannot change. All of the atoms of any single element have the same number of protons. However, you can change the number of neutrons. That's a 0 for neutral. So here we've got 2 atoms. They're both of hydrogen. These are both hydrogen. And what you can see is kind of a molecular shape. The blue is the proton. You can see they both have 1 proton, just like hydrogen does. And then they have a different number of red neutrons, and then they both have 1 electron. So this is normal hydrogen over here on the right. We could draw this as 1 proton, and then in its first electron shell, it has 1 electron. This is something called deuterium. DEU is a prefix that means like second, or it means second, so in this case it means 2. And that's because the atomic weight of this is now doubled because it has a neutron. So deuterium can make heavy water. So if I were to draw this, I would write 1 proton and 1 neutron, and then the first electron shell has 1 electron. So an isotope is any 2 atoms of the same element that have different numbers of neutrons. This is common with carbon. So carbon-12 is the normal version of carbon. This is very common. It's going to have 6 protons and 6 neutrons. Carbon-13 is a little bit rare. This has 6 protons and 7 neutrons. And then we have carbon-14. This is very rare. This is actually radioactive. And this is going to have 6 protons and 8 neutrons. Notice that they all have the same number of protons. If it didn't have 6, it wouldn't be carbon. The only thing I'm changing here is the number of neutrons, and that's changing the overall mass. So this is right here is talking about the mass number, because this is protons plus neutrons. So a radioactive isotope is something that decays. This isotope situation where it's got these extra neutrons is not a particularly stable situation. It's going to tend to give off particles, and when it does, it's going to give off energy, and that energy can be so great that it can actually fluoresce. We use these in science and medicine as radioactive tracers. So you can see up here we've got some MRI images of a brain, and this one on the left is normal. These 3 on the right are abnormal. I believe these are showing different progressions of beta amyloid plaques. So what happens is the radioactive tracer will get taken up by the body and used to build these plaques, and then we can use an MRI to look at the buildup of the plaques, and those usually are an indication of Alzheimer's. You can see there's a radioactive highlight here. So this was using some kind of radioactive tracer that got taken up by what looked like a tumor on the thyroid. This may be a PET scan where they're looking for cancerous tumors. So this is used often if you're going to get any kind of diagnostic imaging test. They're usually going to give you some kind of drink or radioactive isotope beforehand that your body will then take into. Your body uses the radioactive tracers just like the non-radioactive atoms. So if your body's using barium, then it's going to take up the radioactive barium just like a regular molecule of barium. And then that gets incorporated into your body, and then the imaging tools are able to see it fluoresce because it's giving off energy. We also use isotopes in radiometric dating. So this is often called carbon dating. And if you look here, we've got a fossil skull of this saber-toothed tiger looking thing, and it fossilized. When the animal was alive, it had taken up some carbon-14, so that's that radioactive carbon molecule. And when it dies, 100% of its carbon-14 is still present. Over time, it gets degraded, and so we can actually look at what percentage of carbon-14 is left in relationship to carbon-13 and carbon-12, and we can calculate just about how old the fossil is using something called a half-life. So we know the half-life of carbon-14, and a half-life is how long it takes for 50% of it to degrade. So one half-life here to get from 100 to 50, another half-life here to get from 50 to 25, another half-life here to get from 25 to 12.5. And that would be a constant value for carbon-14. And the half-life for chemicals in our body, like if you were to take something like Aleve for a headache, the half-life is going to be on the order of hours, whereas the half-life of carbon-14 is on the order of tens of thousands of years. All right, so we have already mentioned that electrons exist in shells. So if here's my nucleus, N for nucleus, it's got neutrons and protons in it. The first shell here can hold 2 electrons. The second shell can hold 8. And then the third shell here can hold 8. Energy is the capacity to cause change, and we will talk a lot more about energy as we get closer to things like enzymes and metabolism. You've probably heard of potential energy and kinetic energy in the form of physics. So kinetic energy is the energy of motion, whereas potential energy is sometimes called stored energy, or the energy to move. On a molecular level, we also see potential energy, but it's not due to something's height or relationship to the ground. So it's usually due to the position of electrons. If you think about it, electrons are negatively charged, whereas the nucleus of the atom, all of the protons are here. The nucleus of the atom is positively charged. So opposites attract. A negative electron is going to be attracted to a positive proton. So if there's less energy, it's probably going to get pulled in towards the nucleus. An electron with more energy is going to be further out from the nucleus. So here you can see a better drawing of that. This first shell has the lowest level of energy. So if I were to absorb energy, I could go from the first shell to the second shell, assuming I'm an electron. And if I absorb more energy, I can go from the second shell to the third shell, because I've got this negative molecule being pulled away from a positive nucleus. Think about pulling apart 2 really strong magnets. It takes energy to pull them apart. It does not take energy to let them snap back together. So when an electron falls back down, it's losing energy. Usually that energy is lost in the form of heat, sometimes fluorescence. So when you see those radioactive isotopes fluorescing, it's often because they're losing energy. So we know that there are 3 shells that we're going to see. There are more shells, but we're not going to go into that. Save that for chemistry. And any atom, the outermost shell is called the valence shell. So if I have hydrogen, it only has 1 shell with 1 electron. The first shell is my valence shell. If I have something like carbon, there's my nucleus. Carbon has 6 protons and 6 electrons. So it has 2 in the first shell and then 4 in the second shell. So this would have the second shell be the valence shell. The outside shell, this valence shell, is the one that determines an atom's chemical behavior. So both hydrogen and carbon do not have full valence shells. Hydrogen has space here for one more electron, and carbon actually has space here for 4 more electrons, which is why carbon is used so frequently, because it's very apt to bond. So something with an incomplete valence shell, like these two, are going to be chemically reactive. It's most likely going to form some kind of bond in order to fulfill its valence shell. Something like helium, there's its first shell. It's got 2 electrons. Remember, that first shell can only hold 2. So that outer shell is full and it doesn't have any extra electrons to go into a second shell. So it's at full valence shell. So this is going to be chemically inert. When we look at a periodic table and you look at this column over here, these are called the noble gases. That is because all of these fulfill its outermost electron shell. In helium, it's the first shell, neon, it's the second shell, argon, it's the third shell, and so on. We're not going to get to krypton and xenon and radon in this class, but the reason these are so inert is because their valence shell is full, and they're happy. So they don't need any electrons given to them, and they're not going to give away any electrons. And because of this, they are not going to typically form chemical bonds. Here you can see kind of a reduced periodic table. So if you're going to study a periodic table, this would be the one to study. This has got the Lewis dot structures for the electron distribution of the first kind of 3 rows here of molecules that we're definitely going to see. So stuff I would focus on is hydrogen, carbon, nitrogen, and oxygen. Those are our 4 most common. You should be able to understand the chemical properties of how these work. So, for example, oxygen needs 2 more electrons to fill out its valence shell. So oxygen is going to typically form 2 bonds. Nitrogen here is missing 3 electrons. And then carbon, of course, is missing 4. So these are going to typically form that number of bonds, whereas hydrogen here is only missing 1. And so you can see the valence electron shell, that outer shell, is going to determine its chemical reactivity.